All right, let's see if this works now. Testing 1, 2, 3. Testing 1, 2, 3. Should be able to hear me. If you don't hear me, put it in chat, which is impossible. So if you do hear me, put it in chat as well. Oh, Thursdays again. So I hope everything's fine. I'm not getting any feedback from chat. All right, good. My moderator says that she hears me, and that works. That works. Perfect, perfect, perfect. Anyway, Thursdays again. Thursdays again. So warm, so warm. It's gonna be even warmer over the weekend. Like they're saying that it will be above 35 degrees Celsius, and it's already very, very warm. So theory, you should be able to see me now as well. Um, I don't know why the YouTube streaming preview is giving me such a hassle. And like, it also pops up every time this weird suggestion saying that the audio stream's current bitrate is 0. Well, if you can hear me, it's definitely not 0. So, but welcome, welcome. We'll wait another minute before we start, right? Because it's, want to start at 2, but let's hope everything works out. Good, 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 good. So I hope everyone had a good week. I hope everyone was able to do the assignments. The assignments are difficult, I think. I looked over the assignments and I actually cheated on one of them. I had to look up my old answers to see how I did it. Audio and video seem to be out of sync. Yeah, that's what I was thinking as well. I have no idea what's going on there. So it's really out of sync. Let me actually hear the playback for myself. Yeah, that's a little bit out of sync indeed. It's not really, no, no, but we try and be professional here, right? Like that's why I have the like influencer lamp and stuff, and like the nice stream deck setup and everything. I have no idea what's going on. The stream settings are the same as what I did. The only thing which I did is looks like you're a foreign show broadcasted on German television. All right, let's quit the stream and restart the stream then. That's the only thing that I can kind of come up with. I shouldn't have changed the latency while the stream was already connected. I know that that gives issues sometimes for YouTube. It's not an issue on Twitch though. So I'm just gonna stop the stream, restart it, and I hope I don't have to fill in all of the stupid stream information. There's more latency now. Shouldn't be. It might be that because I connected the streaming software already, um, you might be a little bit further behind. Let me just stop the stream and then start it again. See if that fixes it. Okay, I hope I'm back. Hope it's better. There's not a lot of things that I can do on my end. Like when YouTube messes up, it's like I have only like 4 buttons that I can click. And these 4 buttons actually are not controlling any of the latency things. So I'm sorry if it's still bad. Improvement. Okay, that's good. That's good. All right. Good. So let's start then before YouTube starts messing up again. So, regression today. I'm very excited about it. Regression is really my topic. I've been doing regression now for almost 14 years professionally. Try the YMCA. So yeah, no, I've been doing regression now for 14 years professionally, and I have a lot of experience with it. So I hope that people are excited and want to ask a lot of questions. But of course, like always, we're not going to start with the regression lecture. We're going to start with the answers to the assignments. And like I said, I found the assignments really hard. I actually had to cheat on one of them, look at my old answers to kind of figure out what's going on and what I actually wanted. So I hope it was doable for the students, and that everyone was able to do the assignments. Um, so let me pull up my Notepad++ window, and I also need an R window, I think. Yeah, and then I can do this to switch between the two. That all seems to work. Very good, very good. So I already made the file, right? So first things first, if you open up a file and you're going to code, put in a header. Write down what you're going to code. So in this case, it will be the answers to the assignments. Put in your name, and if you are working for a company, also add the company name, because you're being paid by the company. That means that they own half of the intellectual property that you are creating. But the other half is yours, so that's always nice. So good. So nice things is that this time we didn't have to load in any data set. So I don't have to do a set working directory or anything. We just start off with some kind of first assignments that are taken from Project Euler. Project Euler is a really, really good resource if you want to learn how to program. They have assignments. These assignments go from really easy to really, really hard. And generally, the hardest part about programming is figuring out what you want to program. And I found this out myself because sometimes I want to do something, I want to program something, but I have no idea what I want to do. Right? And then you just go to Project Euler and you just look at one of their questions, and generally that helps you, right? Because then you have something that you can work towards. I have a question. Wouldn't it be possible to have this course as an official UBP? Because I'm a biology bachelor student and I think many of my fellow students would be interested in this course as well. The big issue at the Humboldt University is that as a bachelor student, you are officially not allowed to do master courses. That is not entirely true. You are not allowed to do master courses within the same faculty. So as a biology student, you can go to the political science faculty and you can follow a master course there and get it accredited in your UBP. But since the Albrecht Daniel Ter Institute and the Biology Institute are more or less one thing, because they all fall in the Faculty of Life Sciences, you are not allowed to do that. And that is because they want to not have the hassle to check who did certain courses in their bachelor and in their master. Because in theory, you could follow the same course twice, once for your bachelor, once for your master. And of course, it would be easy for them to check, but as people probably have figured out, the Prüfungsbüro here is very, very overloaded. Yeah, I would agree. For me, the earlier you start with programming, the better. I have argued when we had the Studium Reform meetings many, many times that people should start learning how to program directly in their bachelor, and that it is very sad. I don't understand why the university has such a big issue with bachelor student following master courses. It makes no sense to me because the courses should be harder, right? Like a bachelor course generally is easier than a master course. And like in my opinion, the earlier you start with programming, the better it is. So if it would be up to me, everyone would have to follow an R programming course in their bachelor, not as an UWP, but as a Pflichtmodul. So as a required course for your bachelor. But we'll have to see. Like my influence here at the Institute is virtually zero. Yeah, I've dropped the latter weeks ago, and the Prüfungsbureau is still not replying. Hopefully hopefully they do by the second exam date at least. Let me actually show you the exam dates. So yeah, the course is on YouTube, but a lot of people want to follow the course and want to get the credits for it, right? Because as a student, you only have so much time, and based on that time, you want to follow interesting courses. And of course, it's if you don't get any points for it. But there are some ways around it, right? If you are in the last year of your bachelor, you could follow the course in your bachelor and then not do the exam, but do the exam a year later when you are a master student. So you don't have to re-follow the whole course, you just have to do the exam at that point in time. And I am perfectly fine with that. Like, I really don't care about these kinds of constructions. Like, if people follow the course, they learn how to program, I'm more than willing to give people points. But some teachers don't allow that either. So yeah, the first exam is going to be on the 28th of July, and then the re-exam is going to be on the 23rd of September. I think that's the ninth month, right? Points are more important than improving skills. If you want to get your degree, then yes, points are more important than skills. You can be like the best programmer in the world, but if you only have like 36 out of 40 ECTS, then they won't give you your bachelor degree. It's just that simple. You have to get an X amount of points, and that's the way that it works. But yeah, I would totally agree. And all of the bachelor students that try to sign up for the course in their UWP and stuff, I always say that just follow the course on YouTube. You can follow it this year, and then just sign up for the course once you hit your master. And in theory, I can give you a Leistungsschein already, and then you could give the Leistungsschein to the Prüfungsbüro when you are a master student. So there are a lot of ways around it, but none of these ways are really appreciated by the Prüfungsbüro because they are all already overworked, and they don't want to check if people follow the same course twice, because that's their main fear, is that you do the course in your bachelor, get the points for your bachelor, and also do the same course in your master and get the points a second time, which of course would be unfair, right? Because you should do that. So you have the exam, and then you have the re-exam, and I always say the best grade counts. So if you do the exam and you get a 2.3 and you're not happy with that, then you can do the re-exam. If by any chance you mess up on the re-exam and get like a 4, then the original 2.3 of course counts, because like it makes no sense to do a re-exam and then score worse than the original exam. Good. So these are the exam dates. So put them in your agenda, and they will be via Zoom or Moodle. We might do it in person, at least the first exam, but the secondary exam will at least not be given by me. That will be done by Paula, because my contract here ends at the 31st of July, and then 1st of September I will start a new job, if everything goes well, at Northumbria University in the UK. And they decided to make me an associate professor. So graduate sounds wise. Yeah. In the end, like, ECTS is what counts, right? Like, you can get 4.7s on all of your courses, but in the end, if you have enough credits, then you still get your bachelor. Like, in the end, it doesn't matter. Oh my god, news drop. Yeah, well, I hadn't said it before, but so very, very sad about it. I had a really good time here at the HU. I've been doing it here for almost 8 years, or more than 8 years actually. So university didn't want me to make me a professor, and the other university did want to make me a professor. So I'm going to do. Where are you getting your professorship? Oh, I'm going to Northumbria University. So Northumbria University in the UK, which is located in Newcastle. So Newcastle United, go go go. I don't like football, but like, since you're living in Newcastle, you should support the local football club. Newcastle upon Tyne, yeah, that's the official one. So good. But with that out of the way, I think we should start programming a little bit, right? Because that's what we're here for, instead of complaining about how the HU and. So let's not complain. Let's keep it positive, right? Congratulations. Yeah, thanks. I'm really happy about it. So lots of things to still arrange, and go sports. Yeah, any sports. They probably have a good rowing team as well, right? That's very popular at universities in the UK, is do rowing, which is also very popular in the university where I originally come from. Good. So, like I said, Project Euler, very good resource if you don't know what to program. So I took 3 of their questions. I credited them, so they they uh, they get the credits for it. So first question. And the first question is about integer numbers, right? So it's about whole numbers. So I hope that that was clear from the question itself, because if we list all the natural numbers below 10 that are multiples of 3 or 5, we get 3, of course, 5, 6, which is 2 times 3, and we get 9, which is 3 times 3. And then if you sum all of these numbers up, right, then you get 23. Right? Because 3 plus 5 plus 6 plus 9 equals 23. And then the question for you guys was, find the sum of all of the multiples of 3 or 5 below 1,000. Right? So it's not 3 and 5, it's 3 or 5. So there's 2 major ways to answer this. We can answer this using the sec function, or we can answer this using some built-in function which is there, but I always like first going for the sequence, right? So we want all of the numbers that are multiples of 3 below 1,000. So that is actually relatively easy. So I'm just going to create a vector called x3, and I'm going to assign to x3 a sequence from 3, which is the first multiple of 3, all the way up to 999, which is the number which is lower than 1,000, and then I'm just going to step by 3. Right, so I'm just going to make a list of all of the numbers which are multiples of 3. And then I'm going to duplicate this line, and I'm just going to say I'm going to do the same thing for 5. Right, so start at 5, go all the way to 999, step by 5. And now in theory, a lot of people think, okay, so now I can just say, well, I want to combine x3 and x5, and then I just want to get the sum. But of course, this doesn't really work entirely, because the same numbers can be in x3 and in x5. So now, for example, the number 15, which is divisible by 3 and divisible by 5, will be in x3, but it will also be in x5. So the question is how do we solve this? Because we only have to count 15 once and not twice, right? So we can modify this a little bit and say, well, I want to remove the numbers from x3 that are also in x5. So how do I do that? Well, I can just ask which numbers of x3 are located in x5, like this, right? And I can ask which ones those are, and then I'm going to throw them away. So I'm going to say minus, and I'm going to throw them away from x3. And then I'm going to store this x3 as a new variable, or I'm just going to overwrite the variable. And now I can do what I wanted to do, so I can say combine x3 with x5, since now there's no duplicate numbers anymore, and then give me the sum. All right, that's question number 1. So let's go to R, see what actually the answer is. So when we go to R, where's my R window? There's my R window. So the sum should be 233,168, so 233,168. And of course, if you do this question on Project Euler, you would have a little input box. You would fill in your answer, and then you would click check, and then it would check if the number is really the number that it should be. We can actually compare this with other sources, but this is really the correct number. So just throw them away. Of course, you can actually do this a little bit easier. So if we go back to Notepad, then the alternative is to use the built-in unique function, right? So we can just say, okay, so I'm going to draw x3 and x5, and now I'm just going to combine these two together. So I'm going to take x3 and x5, and I'm only going to take the unique values. So if a value occurs twice, only take the first one, and then I'm going to sum them up, right? So this also works, is a little bit cleaner, a little bit like more, but now you're using the unique function, but you can just do it yourself if you wanted to. And this of course gives you the exact same answer. All right, second question. So, each new term in the Fibonacci sequence is generated by adding the previous two terms. By starting with 1 and 2, the first 10 terms will be 1, 2, 3, 5, 8, and so forth. So we did the Fibonacci at the end of the last lecture, and by considering the terms of the Fibonacci sequence, whose values do not exceed 1 million, find the sum of the even valued terms. Right, so there's a lot of things in this question. The first thing what we need to do is find all of the Fibonacci numbers which are smaller than a million. And then what do we want to do? We want to find all of them that are even, so divisible by 2 without any remainder. And then we want to sum all of these things up. So I'm just going to write down a Q2. Hashtag Q2. So first things first, we need to do the Fibonacci sequence, right? So, and I already gave you the code at the last one. So I'm just going to write the fib function, right? So in this case, I want to write Fibonacci is a function, and that takes a number x, which is the index, so the nth Fibonacci or the xth Fibonacci number that we're going to compute. So if x is 1, then we are going to return 1. If x is 2, we are going to return 1 as well, and otherwise we are going to return the Fibonacci number of x minus 1 plus the Fibonacci number of x minus 2, right? So we're just going to ask for the previous two numbers. This is a very bad function. We saw that last time, that it takes a long time to compute the 1 millionth Fibonacci number. But it's good enough, right? So we're of course going to test it. So we're going to say fib1, we're going to say fib2, 3, 4, and we're going to do 5 as well. And then I'm going to put them all on one line using the dot comma so that I can combine multiple statements on one line, just to check if they match up with the numbers that we saw in the example. Right, so I'm just going to copy paste this in, and then we're going to look at the numbers and see if the numbers match up to what we expect. So it's 1, 1, 2, 3, and 5. That seems to be correct, right? And we could check a couple more, but in theory, this is the Fibonacci sequence, so I know that this is correct. Okay, so now we have to find the sum of the even Fibonacci numbers, right? So in this case, if we look at R, then have 1 is not even, 2 is even, so 2 needs to be summed up. 3 doesn't need to be summed up, 5 doesn't need to be summed up. The next one is going to be 8, and 8 is of course even again, so it needs to be summed up. So how are we going to do this? Well, in this case, we don't know which number is the number below 1 million, right? So we have to use a while loop. So we're just going to say x equals 1. So this is the Fibonacci number that we're currently looking at. I'm going to say vipsum is 0, because initially we haven't added up any numbers, right? And then I'm just going to say the Fibonacci number that we are looking at, so fib num, is going to be fib of x, right? Because we need to initialize the number where we're looking at, right? And now I'm just going to say while this vipnum, so the Fibonacci number, is smaller than 1 million, so 1, 2, 3, 1, 2, 3, what am I going to do? Well, I have to check if the number is even, so I can say if the vipnum that we are currently looking at is divisible by 2 without any remainder, right? So when the remainder after dividing by 2 is 0, then the number is even. So at this point, I know that the number is even. Right, so I'm just going to write that down. So I'm just going to print it because I want to have some feedback from the algorithm while it's running. So I'm going to say cut x, so the nth number is, and then I'm just going to say vipnum, right? And then I'm going to add a /new line, so that every time that it finds a new, is there a way to make large numbers more readable? Not in R. I find that very annoying as well. There are programming languages which allow you to do this, so to use underscores to separate the thousands. But R doesn't allow you to do that. But you can use scientific notation, right? So 1 million is 1 times 10 to the power of 6. So I could just say 1e6. And this, of course, is clearer in a way. But it's for anything under like 10 million, I just write it out. But you can use scientific notation. So 1e6, R figures out that this is 1 times 10 to the 6th, so which is a million. So you could write it down like this. But I don't like it also because code highlighting goes a little bit haywire. Maybe for you. How do you mean maybe for you? I just like this. But I always make sure that it's like this, right? So I just like put like a couple of spaces, and then once you check and make sure that it's really the number, you just do it, and you just add it. All right, so and now we're going to go through all of the Fibonacci number. If the Fibonacci is divisible by 2 without any remainder, it means that it's even. I'm going to then print the even number to the screen using the cut function, and I'm going to update my fib sum. Right, so I'm going to say that the fib sum is the fib sum plus the Fibonacci number that I'm currently looking at. And actually someone's calling me on the phone. I am very sorry, I probably have to take this because I will be right back. Interesting, interesting. I'm not even gonna say what they called for. Like, it's just too silly. All right, so if the number is even, right, then we just add it to the current fib sum, right? So don't be like it's sum and num, so there's not a lot of difference in the variable names, but it's good enough, I think, to see. All right, so what do we need to do always, right? Because we do not want to create a for loop, or we don't want to create a while loop which goes on forever and ever and ever, right? So I need to make sure that I move to the next Fibonacci number, right? So I'm going to say x equals x plus 1, and then I'm just going to compute the new number, right? So I'm going to say vipnum is now vip of x. So I'm going to hashtag increase the number, the nth number, right? And then I'm going to compute the Fibonacci number. All right. So now, in theory, it should end at a certain point, right? Because vipnum will become higher and higher and higher. It will print them out, and if it figures out that the number is divisible by 2, it will add it to the sum. We can actually have the sum running in as well, so let's do that, right? So C sum, so the current sum is, and then we can just say vip sum, right? To make it clear that we have the nth Fibonacci number, the value of the number that we have, plus the sum that we are currently looking at. Maybe 1 times 10 to the 6 is clearer for you. It's everyone's personal choice. I like looking at numbers on a scientific notation basis. It's just if you deal with p-values, which are like 1 times 10 to the minus 7 or 1 times 10 to the minus 8, then you kind of quickly get forced because no one wants to see 0.000001. Right? Because then you have to count the number of zeros, and then you have to add 1 to that, and then figure out what the probability was. Good, but So we just build up our function, right? So we define our Fibonacci function, we test to make sure that it's really what we expect it to be. Then we define our variables that we require. We write a little while loop saying that do this until the Fibonacci is below 1 million. Check if it's divisible, but even if it is not divisible, right? Because this part here is outside of the if statement, because we always have to do that. Even if the number is even if the number is odd, we still need to move on to the next number. All right, so let's go to R and let's copy paste this in just to make sure that everything works. So here it starts doing the Fibonacci. So the third Fibonacci is 2, and that the sum at that point is 0. Right? Then the next one that we find, which is even, is 8. So the sum is 2. So of course 8 plus 2 equals 10 for the next time. So the next even Fibonacci number is the 9th one, and that's 34. So you can see that this is regular, right? Because every third Fibonacci number is an even number. And now if we want to know the VIP sum, then we can just type the variable name, and then we see that the VIP sum in total is like 1,089,154. Again, it's a Project Euler question, so if we wanted to check that this number is really the answer, we just put it in Project Euler, we say check, and then it will tell you this is correct or this is wrong. Good, next one. Palindromes. Palindromes are really, really interesting and also really biology related, right? So palindromes are sequences which, when you read it from the front to the back, read the same as when you read it from the back to the front. So in chat, throw your favorite palindrome. There are a lot, and everyone, I think, has their favorite palindrome. So the question that we have is, a palindromic number reads the same both ways. The largest palindrome made from the product of two-digit numbers is 9009, which is 91 times 99. So find the largest palindrome made from the product of two three-digit numbers. Of course, my moderator goes for Anna. That's such an open door. But it's a good palindrome, so I like the palindrome Anna as well. Good, so let's find the largest palindrome for three-digit numbers, right? So the thing that we do here is we take two numbers, we multiply it together, and then we see if it is a palindrome. So we need a function to check if a number is a palindrome, right? So is palindrome is going to be a function which takes a value of x. So the first thing that we need to do is to make sure that the number that we get is really going to be a string, right? So when we multiply two numbers together, we have a numeric value. So I'm first going to say that I want to change this numeric value to be a character value, right? I'm going to say x, and I'm just going to reuse the variable. I'm going to override it. So, but I'm going to make sure that I say as character x, right? So that even if I would input a number, the value of x would be a character. So how do we check if something is a palindrome? Well, the easiest way is to just separate all of the letters from each other and then just reverse it, right? Because if the reverse is the same as the original one, then it's a palindrome, right? Because you can read it the same both ways. So fortunately, R has a reverse function, and we already seen that we can split a character string by using the string split function. So I'm just going to say string split x, right? So split the string into its individual numbers, individual letters. So I'm going to split it by nothing, right? So every time that you find nothing, split it, which means that within either that it will split them all. Another palindrome. I knew a kid, his name was Tim Schmidt. Yes, Tim Schmidt is indeed a palindrome. If you don't include the space, of course. String split expects that we have not one string but multiple strings. So it will always return a list. So in this case, we want to have the first element from the list, right? Because we are only going to give it a single number. We're not going to give it like 5 numbers or 100 numbers that it needs to split. It only needs to split once, one number. So I'm just going to take the first as being the answer. Then I'm going to reverse it, right? So take the vector that comes out and then reverse the vector. And then what I'm going to do is I'm going to use the paste 0 function to paste all of these numbers together, and I'm going to say the separator is nothing, and I'm going to collapse the numbers, or I'm going to collapse the string also using nothing. And then this should be reverse of x. And now I can check, right? Because now if x is the reverse of x, then I need to return true. And of course, if this is not the case, then return false. And this part is a little bit duplicated in a way, because I can just reverse, or I can just return the value of this test, right? Because if this test is true, then it's true, and if this test is false, then it's actually not a palindrome. So I can just say return x is the reverse of x. All right, so let's try our is palindrome, right? So we say is palindrome. So we are going to use Anna. We are going to use Tim Smith, because we know that those are palindromes. And then we're going to use my name as well, which is not a palindrome, just to check, right? You have to check the positives, but you also have to check the negatives when you write code. All right, so let's see if this works. So let's go to R. So we have our is palindrome function, and Anna is indeed determined to be a palindrome. Tim Smith is also determined to be a palindrome. And then we have Danny, which is definitely not a palindrome. So it seems to work. All right, so now we have this function which can tell us if a number is a palindrome. Let's actually try a number as well, right? So let's try 9009, and that is indeed a palindrome. 9006 is not a palindrome, so it checks out, right? The function that we wrote works and is functional. Good. So now we have to do the second part, right? So the idea is to find the largest palindrome made from the product, so the multiplication of two 3-digit numbers. So we're just going to use brute force, right? So I'm going to say for, oh, I'm not typing. So we're going to say for x in 100 to 999, right? Because like there is no, these are all 3-digit numbers. Then I'm going to say for y, which is my second number, in 100 to 999. What do we want to do? Well, we want to multiply them together, so x times y, and then we want to ask, is this a palindrome? Right, so is palindrome x times y. And if this is the case, then we need to remember this one. We need to remember the palindrome, but we also need to remember the 2 digits that created it, right? So I'm going to say xi, yi, right? Initially this is 0, this one is 0, and I am going to say I have the largest palindrome so far. So largest palindrome so far, the LPSF, right? And the largest palindrome so far is also 0. So if these numbers are a palindrome, right, and the largest palindrome so far is smaller than x times y, right, then now I know that I found a number which is larger than the current palindrome. So now I need to remember x, so I'm going to put x in xi. I'm going to put y into yi, and I'm going to remember my palindrome, right? So my latest palindrome so far is going to be x times y. And for good measures, I am also going to cut it to the screen. So I'm going to say x, comma, y, comma, largest palindrome so far, comma, new line, and I'm going to add some spaces to it. So I'm going to say equals, and I'm going to say x multiplied by y is largest palindrome so far. Right, so I'm just going to brute force it. Just going to go through all of the 3-digit numbers for the first number. I'm going to go through all of the 3-digit numbers for the next one. But I have to make sure that every time that I find a number which is a palindrome, that it is actually larger than the largest palindrome that I found so far. I'm going to remember X, going to remember Y. I'm going to update my largest palindrome that I found, and I'm just going to cut it out to screen. And this is, of course, hashtag Q3 for question 3. All right, so let's see if this works. So let's go to R, and let's see if I typed it in correctly. So here we see that it starts like multiplying numbers together, and you see the further we get, the weniger palindromes we find. For some reason, it actually did something weird here. No, it's just still computing. Right, and of course we can check and we can see that all of these numbers are palindromes, and in the end we end up with this being the largest palindrome. Right, so the largest palindrome that we can make from two 3-digit numbers is 906, 609, and we get that when we multiply 913 by 993. Is that clear? I know I'm going through them quite quickly, but we have a lot of exercises so far. So I'm hoping that this is clear, that everyone understood that we first have to write a function which checks if something is a palindrome, which is just done by reversing the input. And then we go through all of the numbers, all of the 3-digit numbers, and then just multiply them together. We check if it's a palindrome, and if it is a palindrome and it's larger than the largest palindrome so far, then we just remember them and we just update. Good. I hope that people were able to do this. Like, these are, I think, the first 3 questions from Project Euler, so they are relatively easy in a way, but they are really hard, right? You can already see that you have to really read the question correctly, and there's a lot hidden in this like 2-sentence question. Right, the largest palindrome made from a product of 2 3-digit numbers. But now we know 906, 609. Good. Question number 4. Hashtag Q4. Okay, write a recursive function to count towards 0. E.g., when starting from 100, it counts to 0. When starting at minus 100, it counts up to 0. All right, so we are going to call this function count to 0, which is a function, and it takes a number. Right, so we need, because it's a recursive function, we need a base case. Right, so the base case here is 0. So if x is 0, we say that we're done, right? So we just return from the function because we're done at that point in time. So otherwise, right, if x is not 0, we need to figure out if the number is larger or smaller than 0. Because in the one case we need to count up, and in the other case we need to count down. So if x is larger than 0, we need to count down. So we are going to return count to 0 of x minus 1. If x is smaller than 0, right, we now have to count up. So we are going to say return count to 0 x plus 1. And of course we want to have a little bit of feedback, so before we do anything we are just going to cut the current number that we're at. So I'm just going to say cut/new line, and to make it a little bit more fun I'm going to add a special print to the base case. So when it reaches the base case it will not print the number, well, it will print a number because the statement here will always be executed. It's not guarded by an if statement. But if we reach 0, I'm just going to say something silly like blast off, right? Like a rocket. I'm going to use a dot comma to keep these 2 statements on the same line, and I added brackets to make sure that the statements are within the if, and I'm going to do that for all of them just so that it's a little bit clearer. Right? In theory we don't have to do this if statement at all. Because, of course, if it is not equal to 0, if it is not larger than 0, then at this point in the code, we know that it's going to be lower than 0. Good, so let's execute the function. So count to 0 of 10, count to 0 of minus 100, right? Or minus 100, like this. So let's see if this works. So we go to R, and we just copy paste it in. So we can see that indeed count to 0, it starts by 10, and then it just goes all the way down, and then says blast off, and then you have here null, which is a little bit ugly, right? Because the null is the thing that is returned, because if we look at the function, we see that we return from the function an empty thing. So for this special situation, R actually has something which is called the invisible return. So you can use invisible to hide the return value. So it will still return a value. What is the difference between using two if statements and one if, between one if and an else if? There is no real difference. It's just clearer to use an else if. And of course, there are some special circumstances. Because here I'm using a return, right? So the return means that it will give something back from the function. So it will never go afterwards, right? If it would not return, right? If it would just say count to 0 minus 1, then it will just execute the function, but then it will just continue. So the else if is kind of a guard against these things. Let me see if I can find or manufacture an example for that. So if we have, for example, a number, right? So we put a number in X. So let's do a random number, so one random number from 0 to 100, and we are going to round this so that there's nothing behind the comma. Right, so now we could have, say, if x, so if x is smaller than 10 and x is smaller than 20, right? So if x is 11 through 19, we want to do something. For example, cut between 10 and 20. Right, so now if we do another if statement, right, saying that if x is larger than 5 and x is smaller than 15, we are going to cut saying between 5 and 15. So here I'm using two if statements. So both of these can be true at the same time. If we use an else if, that is not possible, right? So if I write the same in an if, right? So if I say if x is and now I have to use brackets, of course, just to make sure. I'm going to cut like this, and then I'm going to write an else if, and I'm going to say this, and then I'm going to say the same statement. Right? So these two constructs are not equivalent. This one can fire twice. This one can only fire once. Because if the if statement is true, it will not look at the else if. Because it just, if one of them is true, that's it. Then it fires. And then it just continues after the if statement. So here, of course, like this one can, so if the number that I'm drawing is going to be like 12, right? Then now you will see that the first statement is giving you a slightly different answer than the second one, right? Because the first one is true, so it fires. The second one is also true, so it fires. But when I use the else if, it only fires for the if. Because the if is true, so it doesn't look at the next else if statements. Because you as a programmer should be aware that the first thing that is true that matches is going to be returned. So it's slightly different but the same. So you can use an if and an else, or you can use an if and an else if. But here always the question is do you need to deal with things like overlap or not? So if there's no overlap, then the if statements, two if statements versus an if and an else if statements are equivalent to each other. But if there is overlap between the ranges, for example, that you're testing, then an else if statement is not what you want because it only fires one. So what is the benefit of else? So the else is just to make things very clear. So it's if you do this, else do something else, right? So the else is there to make it clear, and the only reason why in this case we can actually get away with using this here, right, is because I'm returning from the function. So I'm physically ending the function at this point. If I would not be returning from the function, then I should have used an else. But in theory, you would always, if you write an if, you also want to write an else, unless nothing happens for the other case. So, but it's a little bit of a feeling. You will get a feeling for it when you write a lot of if and else statements. Because you can test disjunct things as well in the if and the else statement, right? So you can write, hey, you can draw two numbers and say, if x is between a number, do something, else if y is between. So then if the first one is true, it will never look at the y value. So it will only look at the first one. And the else statement itself is kind of meaningless. I always use multiple ifs. Yeah, and sometimes that is correct. Sometimes that's not really what you want. But generally people dislike writing else if statements. So generally people tend to use multiple if statements. But that is not always correct, because multiple if statements, if you have overlapping ranges, can fire multiple times. And sometimes you don't want that. You just want to check something. If that is true, then don't look at the rest of the statements, because there might be overlap and you might not be interested in the overlap, right? You might want to find the largest range in which a number is located. And you want to check consecutively smaller ranges which overlap with the original range, right? So then you want to return at the point that it's true. But it's really a little bit of a feeling here, because in theory you can always write multiple if statements that do the same thing as a if-else if statement by using else. So, but don't layer them too deeply. Right? If you want to check like 10 different things at the same time, don't say if something, if something, if something, if something, if something, right? Because you don't want to go too deep into your kind of indentation. But it's something that you just have to get a little bit of a feeling for. So yeah, for the blast off function, I use the invisible. So the invisible is the same as return, but it will not print it to the screen. So hey, if we would run it like this, count to 0, and we would go to R, then we would see that now it says, oh, I'm doing something wrong. Count to 0, 10. Yeah, so I'm actually, interestingly enough, I broke my own code. Because that's interesting, because now, because of the if and the else if statement that we just were talking about, right? It actually starts flipping here because it doesn't return. So I have to invisible return. So the return is not the exact, so invisible is not exactly the same as the return, it just makes stuff invisible. But since we were not returning, right? So what is happening when this statement would not be here, right? If I would just say blast off, then it would now check, right? So it would just fall through. And then it starts doing this thing in R where you can see that, well, it says 0, so it says blast off. But then if you look at the code, right, it says blast off. This one doesn't hold because x is not larger than 0. But this one does hold, right? Because I always do this. Since I'm not returning from the function. So it starts going like in an infinite loop going between 0 and 1, right? Because it will update it with 1, then it will see, oh, it's 1, so I have to remove 1, and then I'm going to print blast off. So in this case, it would be much clearer to use the else if. So to say something like this. So if x is do this, right? And then else return this. Right? Because now, even though I'm not returning at this point, it will now not go into this infinite loop. So if we would now do this count to 0 and we would go to R, then now it will go into the infinite loop. Why is that? Because it shouldn't. Oh, wait, I'm having a typo. Yeah, okay. So because of the typo, it still had the old function. So this one needs to go. All right, so let's try this again, right? So we have count to 0. No, don't go into the blast off loop. All right, so now we're using if x equals 0. Else if x is larger than 0, and else do this. Right, so now when I say count to 0, and I give it the number 5, it will say 5, 4, 3, 2, 1, 0, blast off, and it will quit. Because now it doesn't have this the last statement, like these two return statements are now guarded, right? Because if the first statement is true, it will never look at the other ones. So even x could be minus 1 at this point, it will just say, well, if x was 0 at this point, I'm just going to cut blast off, and then I'm going to skip the rest of the code. And by skipping the rest of the code, it ends up with the end of the function, so it will just end the function there. Good. It's something that you just have to play around with. Get a little bit of a feeling for it, like see how it actually works out. But there is a good reason why there are if and else if statements. And that is because of this multiple overlapping problem. Good. Alright, so question number 5. Write your own version of lapply. Make sure to check if the input is a list and throw an error using the stop function if it is not a list. The function signature should look like this. So let's just give you guys the function signature, the way that it should look like. So this is hashtag Q number 5. So I am going to make my lapply, which is a function. It takes x as an input, it takes a function as an input, and then it uses ... So variadic arguments. So, and then there's two ways of doing this, right? So the first thing that we need to do is make sure that x is a list, right? So how do we figure out if something is a list? Well, we can check the class. So if class of x not equals list, then I'm going to stop and say not a list. And now the question is how am I going to implement this function, right? How am I going to implement my own lapply? So my approach was to just do it, right? So just to say, so we have xf, right, which is x after applying f to it. So and the x with the function, and then I'm going to say for x, not x, for I in 1 to the length of x, I'm going to do something. So what am I going to do? Well, I'm going to say, well, apply the function on x at position y, and then call it using the 3 dots. And then I'm just going to say put this in xf, right? So xf at point I is going to be this. And here I'm going to just say, I'm going to pre-allocate the whole vector. So I'm going to just say this is a vector of type list, and it has how many elements? Well, the length of x elements. Right, I'm going to put it in xf, and then once I'm done, so I've iterated through the whole thing, I'm going to just return xf. And now I can test this because I can say my lapply. For example, I want to have a list of 1, 2, 3, 4, 5, and then what do I want to do with this list? I want to apply a function, so I want to apply the plus function. And I want to plus 6, right? Something like this. So let's go to R, see if this works. No idea if this is going to work. Could not find function fun. How is that? Ah, yeah, because it's a character in this case. So I can't use the infix. But when I wrote this code, I was like really puzzling like how to do that. And then one year I had a student, and the student just said, but why not just call the real lapply function? Right? So what the student just did was say, well, return the lapply, so using the real lapply of x using the function using dot dot dot. Right? So don't deal with the implementation just because there is already an lapply function. Right? So why would I rewrite something that already exists? And I think this is the more smart approach. Right? Because now, like, you're just leveraging the fact that there is already an lapply, and the code is really, really like tiny in a way. Right? So it's much better to do it like this than to spend a whole bunch of time trying to write your own mylapply function, because there is already an lapply. Right? So I'm just going to leverage the fact that there is already an lapply, and my lapply function is just going to call this. So of course I can now do the thing that I wanted to do in R, right? Where I just say my lapply so I'm just going to call this now. Same thing. And now we can see if this works, right? Because now I'm just going to leverage the lapply function to make sure that it works. And now you see that it works, right? So instead of being smart and trying to implement it myself, I should have just realized that no, there is already an lapply function. So this is actually my preferred way of doing it now. It's just saying, no, if I'm wanting to write a mylapply function, just leverage the fact that there is already an lapply function. And of course, I do need to check the first thing, right? Because that was explicitly in the assignment. And make sure to check if the input is a list and throw an error if it's not a list. So just check if it's a list and then call the lapply function. What is again the difference between lapply and sapply? I actually have no idea. I never used sapply. I am going to look this one up for you. So I'm going to go to R and I'm going to ask what sapply does. So if I show you guys my Firefox window, this is how it is described by the R help. lapply returns a list of the same length as x, each element of which is the result of applying fun to the corresponding element of x. sapply is a user-friendly version and wrapper of lapply, by default returning a vector, matrix, or if simplify is array, an array if appropriate. By applying simplify to array, sapply xf simplifies false use names as false is the same as lapply xf. So the only thing that it does is that the sapply function calls the unlist function for you, right? And the simplify to array in case you say that you want an array. So the difference would be like this in R, right? So if you use lapply of like list of C 1, 2, 3, 4, 5, right? I want to call the function plus, and I want to add 6 to every element. Now you see that lapply always returns a list, right? The input was a vector, but it returns a list. So if I call sapply, then now you see it's a vector, so it returns a vector. So it's the same thing. It's just that here, in this case, the only thing that it does, it calls unlist for you, right? Because if I do an unlist of the lapply, so it's the same as lapply because internally it uses lapply, but it simplifies it because it just makes sure that if the return value is not supposed to be a list because the input was a vector, it will also make the output a vector. So it's just a convenience function. So there's no really no real reason to use one or the other. The sapply might be more convenient. So Hey Zobe, welcome to the chat. So, same kind of thing. I never used sapply actually. I always use lapply and then deal with the fact that it's a list. And often you actually want it to be a list because it might be that some of the list elements that you give are actually like vectors or matrices. But in theory, they're the same thing, right? So you can see from the help file that it's just a user-friendly wrapper of lapply, and by default it returns a vector, a matrix, or if simplifies array, an array if appropriate. So it's the same thing. Good. So we talked about the fact that you should be smart, right? So in this case, don't start writing your own lapply, just use it. Right? Just use that lapply is there. So when I saw a student doing this, I was like, yeah, this is much, much smarter. Because I had a really, really complex function that deals with like characters and different operands, and I thought, no, it's much better to just say the lapply function exists, so my lapply is just going to call the lapply. Good. Make a function which, as an input, only takes dot dot dot. This function, when called, should print out all the parameters passed to it. All right. So hashtag question number 6. So did I give you guys? No, I didn't give you guys any hints here. So I'm just gonna call this thing dots, right? And it's gonna be a function, and the only input parameter is dot dot dot. And what do we want to do? We want to print out all the parameters passed to it. So, well, the dot dot dot, we can actually do a list of dot dot dot, I think. And then we can just return this, right? Just to make sure that we can test a little bit in R. So let's go to R, right? Make our function. So I'm going to call dots, and I'm going to call A equals 12 and C equals 16. Right, so now you can see that it returns a list, a named list, so A having the value 12, C having the value 16. We can of course make A more complex by including more numbers in it, right? So make a vector of 3 12s, and now we can see that this is the case. So we want to print this out to screen, right? So we can just say, okay, so we have this, instead of returning a list of the dot dot dots, we are just going to make this list. So I'm going to say ml, and I'm just going to say for I in 1 to the length of my list. Well, what do I want to print? Well, I want to say cut, right? So first off, this thing might have a name, so I'm going to say names ml at position I, and then I'm going to do comma, and then I'm going to have a space. I'm going to add an is statement, and then I'm just going to say ml at position y, and then I'm going to do slash new line. Right? I have to remember that this can actually be a vector. So I am going to need to make sure that I paste these things together using, for example, the separator equal to comma. No, separator is nothing, collapse is nothing. Now do commas, right? So make sure that if I have multiple numbers, that you put commas between them all. All right, so let's try this dots function. Right, so now I can say dots. I'm just going to use the old version that I have. So now it says dots is A equals C 12 12 12 and C equals 6 16. Exactly what I want. So let's use the other one as well, where A is 12 and C is 16. We can add more parameters, right? So we can add more, and we can say C, C 16, 16, 16, for example. And then that's the way that we want it. It's a very, very simple function just to get you guys to practice using this dot 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 parameter. Because this dot 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 parameter is important because it is used a lot in plotting functions and variadic functions. Good. So those were the assignments so far. there were 2 additional assignments, right? So we have the recursive function to find the greatest common denominator. I hope that people were able to do that. Just read it up on Wikipedia, right? That's what I said. Just Google the algorithm and then implement it into R because it's on. But I want to show you guys my answer to question number 8. So question number 8 is a hard question which you can spend a long time on, which is a recursive function to draw a tree. Because that's what recursion is really good at. It's really good at making fractals, trees, and these kinds of things. So I just want to show you my answer. So let me actually open up the old answers from last year. And I'm going to show you both of them. So let me just copy paste the code from last year into the notepad window so that you guys can see it. So for hashtag Q8. So they are complex functions, right? So it's a draw tree function which takes an x1 and an x2. So these are the positions at which the 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 the, the current position that we are at. Then it takes an angle. So the angle is if the current line should be angled towards this. Let me actually draw this for you. How it does this. So I need to open up PowerPoint. You know what? We're first gonna have a small break. I just noticed that it's already 10 past 3, so we're going to have like a 10-minute break. When we come back, I will make a really nice drawing for you guys to show you how this recursive draw tree function works. I am going to show you the predified tree already, so that you guys know how beautiful it can look. So here we see a really beautiful tree, fractal tree, drawn with brown and blue colors. Of course, we can define the colors ourselves. But this I just like more alien-looking trees, and you can actually add more trees, right? So you can add a tree because this one starts at 300 0, but it could add a tree here at 100 0 as well. And the nice thing is, I can just call the function again. And if I do that, it will draw a second tree, but this tree will look completely different than the first one. And why is that? This is because it uses random numbers. So it will never draw the same tree twice. And I can add more trees, right? I can put one here at 500 0 as well. So let's do that. So add another one, right? And again, here you see that the tree again looks completely different than the other two. But I'm going to explain to you using my drawing board how this exactly works, and we're going to go through the code because I think it's a really, really fun exercise because people love fractals. And these are fractal trees, and this is actually used in game development a lot to generate these forests with trees, and none of the trees look alike, so they're all a little bit different. And by doing this, you kind of get like an infinite amount of variation just by doing 1 or 2 iterations. So it's used a lot in game development, and I just like how pretty they are because you can change the colors. And hey, you can have the line colors being slightly different. And here we have blue, but we could do the same thing, for example, for a green tree. So you can also, because like these look pretty alien, right? But here we can use green to draw a green tree. Then we can draw another green tree here, and they all look like a little bit different and unique, which makes them very, very nice. I really love doing these kinds of like graphical displays, and people love fractals, so they always look good. First, little break. So, been talking for 1 hour and 11 minutes. So 10-minute break. I hope I'm back before the music ends. I think the first break is going to be birds. And I hope that we didn't have the birds already. But I don't know. I didn't look back all of the old lectures to make sure that I didn't select the same animated gifs again. So I will be back in 10 minutes. I will start the music. And I will see you guys soon. So right. Made it back before the end of the song. Alright, so let's see how we can use recursion to draw these beautiful, beautiful trees in R. Right? So, in theory, it is simple, but in practice, it's a little bit harder. So, let's just take the drawing board. And so, the thing that we're going to do is we're first going to set up a plot window, right? Which we always do. So, let's just draw a kind of basic plot window if the drawing thing will work. So we have a straight line. Oh, that's not a straight line at all. So we have a straight line and we have another straight line. Right, so if you draw a tree, or a stick man for that matter, the thing that you do is you start off with a single line, and generally when you draw a tree, the first line is going to be brownish, which I don't have, so I'm just going to take red, right? So you just draw a line which goes like this, right? And if you then have this first line, then you need another line, right? But we're going to write a function which draws one line. So because of recursion, we can then call the same line drawing again. So we have the first start point, right, which is x comma y, right? And then we have the end point, which is going to be x end comma y end, right? My handwriting is not that beautiful, but these then, the end positions of the first line is going to be the start position of the next line, right? Because the next line is going to be something like this. And we don't have to limit ourselves to calling the function once. We can call it twice or three times with these same start points. So we get something which looks like this if we do it three times. So now we have different end positions again, and for each of these end positions we're going to repeat the process. So the end position is going to be the start position of three new lines, right? And if we do this often enough, and we are going to swap the colors, right? Because we are going to start with a brownish color, and then after doing like the first 2 or 3 layers, we're going to switch colors to something which is green, right? And then we get a tree which looks like this, right? And then if we repeat this often enough, then of course in the end we end up with something which kind of looks already like a tree, right? So already after like 3 or 4 iterations it looks like a tree, but if we continue drawing lines at the end of each other line, then it becomes what you see here in R. Right? So the thing to remember is we're going to write a function which draws a single line, and then after drawing this line, we're going to recall this function 2 or 3 or 4 times, but now with the end position being the start position. All right, so let's go to the code. Right, so the code that I had, so I made 2 versions, right? So the first one is the easiest one because it's not prettified, it doesn't use any colors. So I have x1 and y1. You guys are not looking at the code. So you have x1 and y1, right? So it's a function, so this is the start, the x position start, y position start. And then we have something which is called angle, right? Because we need to have multiple different angles because we can't fix the angle, right? If we look at the drawing, and then here you see that the first one would be drawn at an angle, right? So the first line here would have a certain angle, and this one would have a slightly different angle, and this one will have a slightly different angle as well. So I need to have a parameter where I can set the angle at which I'm going to draw the line, right? So that's where the angle parameter comes in. Then besides the angle parameter, we also have a depth parameter, and the depth parameter is going to be how many of these lines, or how many of these lines did I already have, right? So the first one is going to be at a depth of 1, then this is a depth of 2, this is a depth of 3, and this is a depth of 4, and so on. I'm also going to define something which is the maximum depth. So the maximum depth is going to be how much times do I want to repeat the process before I stop, right? So together, the depth and the maximum depth determine my recursion invariant. And then I have n branch, and this is the number of branches that should come out after I draw a single line. So each line is going to have 3 branches in this case coming out. Right, so the code, when we look at this, is relatively simple. So if the depth is not 0, right, because if the depth is 0, we have to stop. What do I'm going to do? Well, I'm going to take my angle, right, which is just a value between 0 and 365 for being a round circle. I'm going to multiply my angle times pi divided 180 because I need to go from using angles in degrees to using angles in radians, right? Because the sine function takes values from 0 to 2 pi, and because it works in radians and not in angles. And then I'm just going to say, well, take the sine of the angle multiplied by pi divided by 180, and then add that to x1. So x1 is going to be the sine, and x2 is going to be the cosine, because sine plus cosine is always 1. This means that it will always, the length of the branch will always be 1. Right? Because if I add sine of x plus the cosine of the same x, then it ends up being 1. So here I just make 2 ending positions. So I make the x end position and the y end position. And then I'm just going to draw the line, right? I'm going to say x equals, so I'm going to go from x1 to x2, and my y position is going to be from y1 to y2. And then for each of the branches, I'm just going to call the function draw tree again. I am going to say, well, draw the tree, so start at the end position, so at x2, y2. Do 120 times a random value, right? So I do run f1, which is a value between 0 and 1, and then I subtract half. So this would mean that the angle goes from minus 60 to positive 60, right? So because this is from minus 0.5 to plus 0.5 times, and this is to make sure that the branches don't go entirely back, right? Because I want to have like a 60-degree angle in which I am allowed to kind of go up, right? So from if we would look at the drawing, then the thing that I'm doing is saying that I'm limiting at a certain point, I'm limiting the spread like this to a maximum of 60 degrees, right? And the same thing here. So here as well, I'm going to limit it to 60 degrees relative to the angle that it had, just to make sure that I don't get trees which go like this, right? Because if I had a tree which looks like this, then it's not going to be a good tree. So I want the first couple of branches to always go up. And of course, after I've had 3 60 degrees angles, right? Because I can do like this, then I can go 60 degrees, 60 degrees, and 60 degrees. And of course, at a certain point, it can go down, right? But in the first 3 rounds, I want the tree to grow up, and that's why I'm limiting myself to 60 degrees. All right, so then I'm going to just subtract 1 from my depth, because I start at a depth of 0. No, I start at a depth of 15, and I'm going to pass in the max depth, and I'm going to then, for the next round, say, just draw a random number for the number of branches that we're going to do, right? Because initially I start with 3 branches, and here I'm just going to say, no, I'm going to draw a random number, multiply by 5, round this by plus 1, so I can have anywhere from like 0 to from 1 to 6 branches for the next iteration. So let's just show you guys how this looks. So in this case, the setup is a little bit different, right? It's not going to be as pretty as these ones, but the idea is, I think, very clear, right? So here we see the most basic tree that we can draw, right? So it's a single tree with 3 branches. These branches are branching off the tree. Right, so now when we make a new plot, and now we increase our maximum depth to 3, then we see that we get another iteration, right? So here it was unlucky and it only drew 1 branch. Here we have 3 branches, and here we have 4 branches, right? We can reset the plot, and then we can say, well, go to 6 levels of iteration, right? Then you see that it starts to become like a crop, like a tree. And of course, we can just continue this, and we can play a little bit with the numbers. We can say, well, we want to not start at an angle of 15 degrees, but we want to start at an angle of 35 degrees, right? And then hey, you can see that the first one goes like this, and then it draws two branches, so it gets this weird-ish shape. But that's kind of how the tree drawing function worked. And you can spend a lot of time making this like really pretty. You can kind of play with the angles, and the other version that I had. So if we go back to Notepad, right? So the secondary version, which is prettified with colors, it also draws a random color. But if the depth is larger than 5, and then I'm going to make it brown, and I'm going to make like a little bit bigger lines. But in theory, it's the exact same thing. I limit myself here to 30-degree angles, which is also based on the number of branches. So the more branches I draw, the more freedom I allow for the tree. And in the end, you can spend a lot of time on it. You can make all of these parameters as well. You can say, well, I want to have, for example, blue trees or orange trees or green trees. But the nice thing is that they look absolutely stunning. At least I think that they look absolutely beautiful. And in this case, I could update the plot window a little bit, saying that go to like 400 and draw my tree, right? And you can see that it draws a tree. It looks like a tree. I can put another tree into the same figure, and I can create like really nice looking forest and nice looking trees. So very common technique used in computer graphics, used in computer in games, to create random looking structures which are more or less dynamically generated, and never look the same twice. Of course, I can make them look exactly the same by setting my seed, but this is a very common technique. So if you didn't do this assignment, that's perfectly fine, but do spend a little bit of time trying to understand how it works. I hope that my drawing made it a little bit clear to kind of show you guys how you want to build it up, right? So you just make a function which draws a single line using a random angle, and then hey, it calls the same function an X amount of time for each of the branches, and each of the branches does the same thing. But of course, we have to stop somewhere, so that's why we need this recursion invariant. Very fun, very fun. I really love it. Good. On to the lecture for today. So today we are going to talk about regression. So, like I said, I have a lot of experience with regression, so feel free to ask any questions. The regression lecture was online as well for last year, and I do love doing this lecture. So regression is one of these core techniques in machine learning, in AI. It is a core technique in doing predictions. So if you ever want to do like stock market predictions or other things, then you're forced to deal with regression. I already gave you guys the exam dates. So what am I going to talk about? I'm going to talk about a little bit about the basics of regression. So when can we do regression? Then I want to show you guys single linear regression and go a little bit more in detail on how to calculate things like critical values and p-values. And then we will discuss different types of linear regression, like multiple linear regression and quadratic regression. And I wanted to say some things about model selection, since when you are building models to describe reality, you have to have a way to compare these models against each other in an unbiased way. So, like I said, ask questions. It's just a basic introduction how to do basic linear regression in R using the linear model function and the ANOVA. So we're going to build linear models, and we are going to use ANOVA, analysis of variance, to figure out how good our model is fitting to the data that we have. I have a lot of experience, I already said that. I try to keep the lecture short, and that is since otherwise we would sit here until like 10 in the evening. So next week we'll be doing linear mixed models, and the week after we will be doing generalized linear mixed models. And of course, ask any unrelated questions for any details if you want more details. So here you see the field of regression. All of these things are called linear models, regression models. So we have things like ANOVA, analysis of covariance, multiple linear regression. We have time series analysis, which is called ARIMA. We have nonlinear time series. We have generalized linear models when things are not normal distributions. So today we will be talking about this part of this whole field. Next week we will be talking about repeated measurements models, and the week afterwards we will be talking about generalized linear models. So 3 whole lectures about regression. So very basically, regression is to estimate the relationship among variables, among measurements that you did. So it is used to do predictions. That is the goal of regression. The goal of regression is to figure out how variables are connected to each other and how we can exploit these correlations between variables or these covariances between variables to do predictions so that we know when to buy stocks to make money, or so that we know um, when to do a treatment, right, for the biggest effect. So there are many techniques for analyzing several variable models. Like I showed you guys, the field of regression is really big. But always the focus is on the relationship between the dependent variable and one or more independent variables. So the dependent variable is the outcome or the effect. It is the thing that we want to predict. And the independent variables are the input or the cause. So it is the variables that we assume are controlling the dependent variable, right? So they are more or less the things that we use for our prediction. So in a regression model, we have several variables. So the basic regression model looks like this. So we have y, which is our dependent variable, is linearly related to some function of x, which are the independent variables, and betas, unknown parameters. So the unknown parameters are the things that we want to know. We want to know if the temperature increases with 5 degrees Celsius, how does the likelihood of getting rain change? Or if the temperature rises 2 degrees Celsius, how does this affect the sale of ice cream, right? So we might be interested in investing in ice cream stocks. So we have a couple of constants as well. So we have n, which is the number of independent measurements that we did. So it is the amount of, for example, individuals that we measured, or the amount of data, or the amount of time points that we use to measure ice cream sales. And then we have k, and k is the number of unknown parameters that we are estimating, right? So the independent measurements here are what gives us power, and k is what takes away power, right? We can, for example, if we only look at the temperature to predict ice cream sales, we have one unknown parameter. So k is 1, and n is the number of days on which we measured our ice cream sale and the temperature. But we can include much more, right? We can look at the temperature, but also if it is raining or not, if it is a Monday, and, well, any other things that we might think would affect sales of ice creams, right? So the most basic regression model means that we are looking at a dependent variable which is controlled, or which we think is controlled by a number of independent variables, so things that we can influence generally. And for each of these independent variables, we want to estimate something called beta, and beta is more or less the directional coefficient, so the relationship between when you put the independent variable on the x-axis and the dependent variable on the y-axis. So in regression, we always talk about statistical power, right? So when n, so the number of observations that we have, is larger than k, and the measurement errors are a normal distribution, then we call this the excess of information. So the power, the statistical power that we have to estimate these beta parameters depends on two things and two things only. The number of individuals that we have observed and the number of parameters that we are trying to estimate. So n minus k is called the excess of information, so it gives us this power to make statistical predictions about the unknown parameters. When we do regression, especially when we do basic linear regression with a normality assumption, we have a lot of assumptions. And in blue, I highlight the most important assumptions that need to hold for a model to be valid. All of them have to hold for the model to be valid, but the blue ones are the ones that go wrong the most often, right? So when I'm reviewing papers, I always check, if people do linear regression, if these 4 or 3 major assumptions hold, and I also will check if the other assumptions are more or less satisfied, but I'm not going to complain about them in much detail. I am going to complain if one of the blue ones is not satisfied. So the first one is the one that goes goes wrong the most often, right? So the assumption here is that the sample you are looking at is representative of the population that you are trying to infer a prediction for. So when I think about human genetics, I see this going wrong all of the time, because they will do a certain study and they will look at patients that arrived at the hospital. Because if you're a human geneticist, you generally work at a hospital. So the people that are in your random sample are patients walking into the hospital. But people walking into the hospital is not a representative subset of the population. It is not a random draw. People going to the hospital are sick. And generally, you want to make predictions for people who are sick or not sick. But because your initial random sample that you take is people walking into the hospital who are sick or who think that they are sick, all of your statistics that you are using is only going to tell you something about people walking into your hospital, right? It's the same as when people do studies on a certain area, right? So they for example, want to know if a certain drug is having an influence on a certain disease. So they are going to have a hospital where some people get the drug, other people get the placebo. But this hospital is, for example, located in Germany. And then their conclusion in their paper is, this drug increases your chance of surviving cancer. But they fail to mention that their sample is only representative for people living nearby this one hospital in Germany where they did this study, right? So if you look at big studies that are being done by, for example, Pfizer or other big companies, they measure these effects, so they give their drugs and their placebos to people all over the world, people who have different cultural background, different heritage, and that is required. Because you cannot only look at a small German population and then extrapolate your findings to a larger population, like humans, right? Humans are very diverse, and Germans in general, or Europeans in general, are just a subset of all of them. So the first one is the one that goes wrong the most often. The sample that you are doing your prediction on needs to be representative of the population. The next assumption is the error. So in linear modeling, we have no assumption on the input. So our dependent variable, our y, can have any distribution that we want. The normality assumption in linear regression is on the error term. So the error is a random variable with a mean of 0 conditional on the explanatory variables. So after we fit all of our different parameters in our model, we look at the error, and the error needs to be a Gaussian distribution with a mean of 0. The original input distribution doesn't have to be. This is different from a t-test. In a t-test, the original distribution that you input needs to be a normal distribution. In linear regression, there is a normality assumption, but the normality assumption does not hold for the dependent variable. It holds, or it should hold, for the error term. So after removing all of the effects that we are trying to estimate, the remaining, the residual variance, should be a normal distribution with a mean of 0. The next one is not that hard. The independent variables are measured with no error. And of course, this is impossible. You cannot measure things without an error. But it is an assumption for linear modeling. So the only thing that you can learn from that is that all models are wrong. Because you cannot measure something without an error. Right? If I'm just measuring body weight, then body weight will, like, the scale that I'm using doesn't have infinite precision. And that is not bad. It only means that you have to do your utmost best to not have an error, right? So when you are measuring people, you should not use a scale which is accurate to 50 kilograms. You should use a scale which is accurate to like 2 digits behind the comma. If you're measuring mice, the body weight of mice is much, much less. You need more than 2 digits behind the comma, because mice are generally in the order of like 10 to 40 grams. So having a scale which tells you that this is like somewhere between like 0 and 100 gram is not going to be proper, right? But you cannot measure independent variables with no error. But the assumption is that they are measured without any error. So you cannot satisfy this assumption even if you wanted to. The predictors are linearly independent. It is not possible to express any predictor as a linear combination of the others. And this goes wrong all of the time. And this is because we live in the real world and things are correlated to each other. For example, the temperature outside and the amount of precipitation from a cloud are correlated to each other. So in theory, when you're predicting something about atmospheric conditions and you are using the temperature and the amount of precipitation into the same model, so for example, you say the number of hailstones I observed on the ground is determined by the temperature plus the precipitation plus some other factors, then these two things are not completely uncorrelated, because the precipitation is tied to the temperature that you are observing. Errors are uncorrelated. That means that when I look at the error terms, also the error term is not correlated to any of the predictors or to the dependent variable. The variance of the data should be approximately equal across the range of your predicted values, and this is called homoscedasticity, or the absence of heteroscedasticity. And if this is not the case, you can log transform your input data. So how does this look? Let's just go back to the drawing board. Since I've not been using it too often, I want to have actually a new drawing. So let's just give me a new drawing. Drawing time. Right, so homoscedasticity or heteroscedasticity is a relatively difficult concept, but with one picture I can explain to you what that means. Right, so when we have our measurement values, what we don't want to happen is that there is a bigger error the higher the values become. Right, so here we can see that the more increase in x there is, right? So if we look at the increase in x, we see that in y the variance becomes bigger and bigger and bigger. And this is called heteroscedasticity. And we don't want that. Because if we now fit the best fitting line, right, then you can see, let me use another color for the best fitting line. Let's use, what's going on? Let's use green, right, like this. So now we see that the errors, so here are very small, but the errors here are very large. So there is a correlation between the error term that we observe and between the x, so between our predictor variable. And this is called heteroscedasticity, and we don't want that. If we see something like this happening, generally what you will do is you will take a log transformation of your data. And that is actually the reason why, for example, microarray data is log transformed. Because you see this heteroscedasticity if you look at the larger values on the microarray. Because the larger intensities just have more variance than the lower intensities on the array. And this just has to do with the law of big numbers. And the bigger a number, the harder it is to measure this number exactly. So those are the assumptions. But check the blue ones. So if you ever need to review a paper and they do linear regression, make sure that you check at least the 3 blue ones and make sure that those hold. Good. So in R, regression is done via the LM function, or not so much the regression itself, but the linear model is done via the LM function. So here we are using the air quality data set. So I'm first loading data air quality, and air quality is a data set which has ozone measurement, temperature measurement, and it has some other measurement as well. So it has the wind speed and some other measurements that we can look at. So the most basic model that I can build using linear regression in this case is to say that the ozone concentration, which is observed in the air, is dependent on the temperature that we have at this day. Right, so, and then I do my linear model. So I say make a linear model where we regress the ozone temperature, or the ozone concentration on the air temperature. And then I'm going to say, comma, data is air quality. So here I'm specifying where the ozone column is and where the temperature column is. So air quality just has a column called ozone and a column called temp. And then I have my lm.temp, and then I'm just going to type summary lmtemp, and then it will give me the overview. It will give me the summary of the model. So how does this look? Well, it will print out the formula that you used, it will give you the residuals, and it will give you the coefficients. So you see here that there are 2 coefficients. There is the intercept and there is the temperature, right? So when the temperature is 0, the ozone concentration is expected to be negative 146. And then for every degree in temperature rise, the ozone concentration will increase with 2.4 units. This is what the estimate means. And we see here that both of these effects are very significant, right, with the 3 stars. And it tells you here that the multiple R square of the model is 0.48. So that means that around 48% of the variance in the ozone concentration is caught by this temperature coefficient. So how do we now plot this, right? If we want to see what's going on, we can plot the air quality, the ozone column versus the temperature column, and I'm plotting them here in blue using solid points, and I'm getting the coefficients out. So I'm getting the temperature, so I'm getting the intercept, which is where the x is equals y line is, right? So you can see that when the temperature is around 60 degrees Fahrenheit, the ozone concentration is very low, around 0. When the temperature is around 90 degrees Fahrenheit, the ozone concentration is around like 60 to 70. And you see that there's also variance in our data. So if I want to plot this best fit line, I'm just going to take the intercept out, and I'm going to take the temperature out of the 2 coefficients, right? So here the A coefficient will be minus 146, and the B coefficient will be 2.42, right? And then I'm just going to add the best fitting line to my data, saying draw a line, the alpha coefficient of the line is going to be A, and the beta coefficient of my line is going to be B. Make the line red and plot it in my data, right? And you can see that this model fits the data relatively well, right? A lot of the variance is explained by this one line that we draw through the data. Of course, when we look at the model, right, it tells us that we have standard errors, right? So it is not exactly able to identify with 100% certainty where the intercept is going to be or what the exact influence is going to be of temperature, right? So we have always an error in the prediction. So if we want to calculate the confidence interval The confidence interval means that 95% of the data should be more or less inside of the confidence interval. We have to do a couple of steps in computing ourselves. And of course, R can do this for you as well, but I actually wanted to show you guys how you can do this by hand. So what we want to do is we want to calculate the margin of error. So in standard regression, in standard single linear regression, we can use the t-statistic. So this is the t-distribution from the t-test. So it needs the standard error, which we can get from the LM summary, right? Because it just gives us the standard error for both of the parameters. What we also need is the critical value, right? So the critical value is the probability boundary that we are assigning to it. So in our case, because we work in biology, our standard probability boundary is an alpha value of 5%. However, if we don't know if the parameter that we are estimating is going to have a positive influence or a negative influence, we have to do a two-sided test, just like with the single-sided t-test versus the two-sided t-test. So what we have to do is we have to do two-sided, which means that we have to say we divide our alpha by 2, and then we say 1 minus the alpha, and so we are dealing with 0.975, which is more or less two-sided of the t-test. We need to know our degrees of freedom, which is n, which is again the number of independent observations minus 2. Why minus 2? That's just the case. I'm not going to explain degrees of freedom. They will come back. But the degrees of freedom are more or less the statistical power that you have. And we do minus 2 here because we have two parameters that we estimated. Right? So the first parameter that we estimated is the intercept, and the second parameter that we estimated is the slope of the temperature coefficient. Right? So that is why we subtract 2, because after fitting these two values, the intercept and the slope, only n minus 2 observations are independent. 2 of them are fixed because we calculated two numbers. The critical value here we can calculate, so we just say we take the t-distribution, so we take the quantile t-distribution, we fill in our probability boundary that we want to have, which is 0.975, and we have n minus 2 degrees of freedom. And this call in R will just give us the critical value. And the margin of error is defined as the critical value times the standard error. So the standard error we can get from the summary, the critical value we can calculate based on the number of observations that we have, and the probability boundary that we want to have. So we can calculate a 95% confidence interval, but we can also calculate a 99.9% confidence interval. Right? That would just mean that instead of having an alpha of 0.05, we go to an alpha which is 0.0001. Right? So we can be as stringent as we want. So the margin of error is the critical value times the standard error. So in our example, we can take the summary. I'm calling this lm.sum, and I'm going to take both coefficients, the temperature coefficients and the standard error from this coefficient. Right, so the standard error from the temperature coefficient is the one that I want to have. So, and that has a standard error of 0.233. Right, so that's this number here, 0.233. Right, because I'm not going to look at the intercept at this point. I just want to know what is the confidence interval of the temperature, because we can do the same thing for the intercept, but we're not really interested in the intercept that much. Right, I can now calculate my own critical value, which is just the number of rows in the air quality data set, because every row is an independent observation. I subtract 2 because we calculated a beta for the temperature and we calculated the intercept. And then this gives me that the t statistic at this point is 1.975. So I can calculate my margin of error on the coefficient that I computed, and if I do that, I just multiply the standard error versus the critical value. So I'm saying that's 0.46. Right, so the confidence interval that I'm having means that the temperature coefficient, the real value of the temperature coefficient, is going to be as low as 1.97 all the way up to 2.98. Right, and of course the estimated parameter was 2.42, which is exactly in the middle. Right, we have just as much error on the bottom as that we have on the top. Good. So this is the real value is going to be between these two numbers, right? So now we know. So I can actually plot the confidence interval as well, right? So I can say, well, I can use a prediction to predict the values of the ozone using the temperature. So I'm just going to say I'm going to make a range on which I want to predict. And this is going to be from the minimum temperature of my model to the maximum temperature of my model, right? So if we look at the plot, this is going to range from like around like 55 all the way up to like 100 point something, right? So I'm just going to say do a prediction over the whole range in which I have observed data, right? So that's what I'm doing here. Then I'm making a data frame of it because the predict function takes a data frame. So because this is a vector, but the predict function takes a data frame with the data in the columns. So I'm just going to say make a data frame where the temperature is the P range, pi is 1. That's not that interesting. Oh, wait, this actually, let me actually fix the slide because that's wrong. Something went wrong here because the by parameter of course belongs to the sec function, right? So I'm going to say from the minimum to the maximum by 1. All right, let's go back, right? So I'm just going to say for each F4 I'm going to do a prediction from the minimum temperature for 55 degrees. I'm going to do a prediction from 56, 57, 58. So it's just a sequence, right? And I'm going to then make a data frame which has one column called temperature, and I'm just going to call the predict function. So the predict function as the first parameter takes the linear model in which it needs to do the prediction. So it takes the linear model. It takes the new values, which in our case is the range from the minimum to the maximum. I'm going to say I want to have the confidence interval. So int is C for confidence. And I'm going to want to have the 95% confidence interval. I'm going to make a plot. And I'm just going to plot the values of the temperature versus the ozone. And then I'm going to add the regression line, so the regression slope, so the standard, so the fit. So I'm going to get that from my prediction, and I'm going to have the upper limit and the lower limit, which I'm going to plot. So of course this is a lot of work. Like you can see that we have to do our own prediction, and then using this prediction we can plot the confidence interval on top of our data that we have. We could also just use an external library. There's many libraries that can use this or can do this. So you can use the visreg library in R to do the same thing. So when we then look at it, we see that we see now our regression line, we see our confidence interval, and now 95% of the data is between this confidence interval. And then you guys will say, but that's not the case, Danny. Like, you are completely crazy. 95% of the data is not within the blue lines or here within the gray area. And why is this not the case? Because my model is not perfect. My model had an R-square of only 48%, which means that 95% of 48% is going to be within the lines, right? So in this case, like 1 in 4 values is going to be within the confidence interval. Just as a, like, because that's important, right? Because always people ask me like, but your confidence intervals are way too narrow because it doesn't contain 95% of the data. It does not contain 95% of the observed data, because the observed data is of course only predicted by this model for 48%. So in the end we have 95% of 48% being within these lines. So we expect like slightly less than half of the dots to be within the confidence interval. And you can see that the confidence interval is not the same. So the width of the confidence interval is smaller in the middle than it is at the edges. And why is that? Well, that is because when we do the estimate of the parameter, right? Just screw this out, right? So we have our x values and we have our y values, right? So if in this case we have the temperature on the one axis, still writing with green, and here we have our ozone, right? And we have our values, which kind of go like this, right? So these are our observed values, and then we have our regression line, right? But the regression line has a directional coefficient. And we just learned that this directional coefficient can be as high as like 2.8, but as low as like 1.7 or 1.4, I think, right? And when you would draw all possible regression lines in your data, right, then you see that what starts happening is that there is a kind of that the middle, in the middle, the confidence interval is smaller than it is at the edges because of the variance in slope, right? So the confidence interval that you observe in your data is nothing more than an infinite amount of regression lines between the standard margin of error that we originally calculated, right? So between minus 1.97 all the way up to 2.89. Right, so it's just all of these lines, and because of the fact that the way that lines work in the middle, that creates a smaller confidence interval than at the edges. Good. How do we now figure out how good our model is? Right, so we can look at the residuals. So the residuals is the variance which is left over after fitting the effects. Right, so this is a measure of how well the regression line fits the data. So the aim of regression is to minimize the sum of square of the residuals. And the sum of square is the difference, is the square difference between the observation and the mean of the observation. So in our case, it's the sum of squares of the observed value relative to the predicted value that we have. Right, so our predicted value is just a straight line. So this minimizing the sum of square means that we want to make, or we want to have a line which is as close to the individual dots as possible. So we want to minimize this sum of square. And if we do this, then what we are doing is we are fitting a maximum likelihood model. So how do we visualize the residuals? Well, residuals are easiest on clean data, which means that no NAs should be in the data, because of course when we have an observation, or if we have an ozone observation which is NA, we cannot calculate the sum of square because we cannot take the observation minus the prediction value. But the same thing holds for when, for example, the temperature is missing. Right? We cannot do a prediction when we have a missing value. So the first thing that I'm going to do is just say remove all of the NAs from the ozone and head, because the ozone measurement has some missing values. So I'm just going to make a new clean data set which has no rows which are missing. So I'm going to do my linear model based on my clean data. I'm going to do my prediction, right? So I have an LM temp model and I have an LM temp clean, and then what I'm going to do is I'm going to plot the air quality clean, the temperature, versus the ozone. So that's just the observed data that we already saw. I'm going to put in the regression line from my model, and then what I'm going to do is I'm going to say for I in 1 to the number of rows of the air quality clean, I want to draw a line from the observed data point towards the predicted data point, right? So the air quality clean temperature. So the prediction that I'm doing here is not having an additional input. I'm just going, when you don't provide a range to predict across, it will just do a prediction for each of the observed temperature values. So I'm just going to draw lines for each of the temperature points to the ozone to the prediction that I had. Right, so from the real observed value to the predicted value, and I'm going to do that in blue. So this is how our residuals look like, right? So we have an observation here while the prediction was all the way here. We have some observations here while the prediction was here. So minimizing the sum of square means that we take the square of this number, because this is a number. All of these things are in theory numbers, like here we go from like 40 all the way down to like 0, so this is 40, so here we have 40 squared. 20 squared, 10 squared. Here we have minus 20. If we square that, it becomes positive, right? So we sum up all of these numbers together, and that is the sum of squares. It is the amount of variance which is left after we fitted our line. It's the squared variance. Good. Let's take a break here. Are there any questions so far about single linear regression? Because we already discussed a lot, right? We discussed how you can fit it using the LM function. You can use the predict function to do a prediction based on your model. We already talked about confidence intervals on how these relate to the data that we have and how these relate to the estimated parameters. And we also talked about residuals and what are residuals of our data. So I'm going to wait a little bit because there's always a little bit of a delay on YouTube. So if there's no questions, which is fine, then we are going to go to the second break. I forgot which animal I picked for the second break, but you'll figure out soon enough when I start the break. Good, so there's no questions so far, so I hope that everything's clear. So if I ask what is a residual, what do we want to minimize, then you guys can answer these questions on the exam, which is perfectly good, because it is a relatively difficult concept to deal with, regression. And it's not a solved issue at all. Like, there's people that work in data analysis and optimizing regression their entire life. So it's one of these active fields of research within science. Good, but that being said, enjoy the second break. I'm going to start the music, and then I'm going to switch to the second break, and we'll be back in like 5 to 10 minutes. I made it back again. I hope everyone's still awake and not cooking inside like I am. Like, the temperature is just getting crazy here. Getting crazy. Alright, so around 40 minutes left. We still have like more than half of the slides to go. So I'm gonna speed up a little bit, but I think that once you understand the basics of regression, multiple linear regression is actually quite easy. Because, of course, we don't just have the temperature measured, right? We might have wind speed measured, the month, the day, the solar radiation currently. So there's a lot of different things that can predict the ozone temperature that we have. So when I look at the head of the air quality data set, we can see that we have our ozone, but we also have different things that we can use for our predictions. So when we have multiple linear regression, we have a mathematical model with, for example, two factors. So we have the alpha here, which is our intercept. Then we have our first directional coefficient for the first parameter that we're estimating, for example, temperature. And then we have our second unknown parameter, our beta 2, which is controlling, or which is giving us the influence of the second variable. You can generalize this to, of course, as many variables as you have. So, for example, if we model the ozone as a function of temperature and wind, then we get ozone being our dependent variable. We have the intercept, we have the temperature, and the wind as the two dependent variables that we are looking at. And of course, we now have to estimate two betas and a single intercept. So in R, nothing much changes. We can use the LM function again. So we say that the ozone is a function using the tilde of temperature plus wind. We fit it using the air quality data set. And then we just look at our summary, right? And we get, again, our estimated intercept. We get the parameter for temperature, which has changed. And we have now an estimate for the wind. Furthermore, we see that the model fits better. Right, 56.8% of the variance in our ozone concentration is explained by this model. So compared to our first model, which explained 48%, this model explains 50% of the observed variation. And the thing to notice here is that the estimate for temperature changed slightly. Right, so the initial estimate was that for every increase of degree Fahrenheit for every degree increase Fahrenheit, we have 2.4 units more ozone, but now we have an estimate of 1.84. And this is because there's, of course, a relationship between wind and temperature as well. So the wind takes a part of the variance, which is explained by the temperature, and this is distributed to the two terms. Right, so again, we can plot the observed values versus our estimated values if we wanted to. And so in this case, I'm using the width function so that I don't have to type air quality all of the time. So I'm just going to do a prediction using our new linear model. I'm going to make a list in which I provide the temperature and the wind speeds. So I'm only going to do a prediction when we had this temperature and the wind measurement. So I'm going to plot, and then I'm just going to add points. So the plot is the black dots, so those are the observed values, and in red I'm going to add the predicted values to our graphic. Right, so again, we look at the temperature axis and we look at the ozone axis. Of course, I could have looked at the wind axis as well, but in this case, I think it more logical to come from the temperature side because the original model that we used was also based only on the temperature. But these are the predicted values when we have the wind and the ozone, the wind and the temperature in our model. So you can see that this seems to fit already a lot better than the single straight line that we originally had. So we can also add interactions to our model. So an interaction means that we have an x1, which might be temperature, we have the x2, which might be the wind observation, and then we want to say that there's an interaction between the two. It might be that at higher wind speeds the temperature has a bigger effect, or at lower wind speed the temperature has a bigger effect. So we just have an unknown parameter, an additional unknown parameter, which is multiplied to the interaction term, to x1 multiplied with x2. So in our example here, when we use temperature and wind, we can add an interaction term. In R, we use the double point for interaction terms into the model. So again, is there an interaction between wind and temperature? So we just pose the following model, saying we have a linear model where the ozone is controlled by the temperature, by the wind speed, and the interaction between temperature and wind. We do the summary function, and again we see that our estimates have changed. The temperature now has a much bigger influence all of a sudden. The wind also has an influence of 14, and the interaction between the two is slightly negative. We actually see the probability values, so all of these terms are highly significant, so that means that yes, there is a significant interaction between temperature and wind when we are predicting our ozone concentration in the air. Again, we have a better multiple r squared because, of course, the more parameters we put in our model, the better the model fits. And in this case, our model explains 62.6%. Right, so adding the interaction compared to our first model, which explains 48%, the second model explains 56%, and this model with the interaction term now explains 62% of the observed variance. Again, estimate that the temperature has changed. The original estimate was 1.84, and now the estimate is that there's 4.07. And this is, of course, because the interaction term is very collinear with both the wind and the temperature. So it will absorb some of the variance of the data, gets not assigned to the main effects, but to the interaction between the two main effects. Good. So when we talk about linear models, people always think about straight lines. But that is not true, because we can also talk about quadratic linear regression. Linearity or linear regression means that a change in one of the independent variables always yields a corresponding change in the response variable. Right? So people always think about the standard formula for a straight line, saying y equals the intercept plus a certain unknown parameter, a certain beta, times a main effect that we are looking at. However, the following functions are also linear functions, because every increase in x will have a corresponding increase in y, right? So if we look at the following formula, where we say we have a formula where our ozone is predicted by an intercept plus a beta coefficient times x to the power of 2. Right? So we take the power, the second power of x. And this, although x now is not linear in the sense of a straight line, because it's now a curved line, right? It's now to the power of 2. This is still a linear model. The same thing holds when we do something like y equals the intercept plus e, so the base of the natural logarithm, to the power of the beta 1 times x. Right? Here we see beta 1x, which is a linear effect, and if we take e to the power of a linear effect, the effect itself still continues to be linear. So in R, we can also do quadratic regression, right? We can fit quadratic regression, but we can also fit this kind of e to the power of regression coefficient. So how do we do x to the power of 2? Well, imagine that in our mathematical model, we actually assume that there is actually the temperature has an effect, but the second power of temperature also has an effect, right? Then we can write down the following model saying that the ozone is the intercept plus the temperature to the power of 1. So we have a single beta that we estimate, and we have a secondary beta that we estimate for temperature to the power of 2. So in R, we use this, floating head thingy for quadratic regression. However, we need to surround the statement using the I function. And this just has to do with the way how linear regression works in R. It's nothing magical, but just remember that every time that you want to fit a quadratic term or a term to the power of 3 or to the power of 4, you have to make sure that you do this term and you use the identity function before you put it into the model. So how do we specify a model like this in R? Well, again, we can say we have a summary of a linear model where we say that the ozone concentration in the air is determined by the temperature plus I temperature to the power of 2. Again, we use the air quality data, and now we see that we get the formula back, we get again our coefficients with the estimates, and again we see that there's a significant interaction of the temperature to the power of 2, which kind of we already saw when you looked at the data, right? The data does seem to not be an exact straight line, it seems to be kind of a quadratic curve. Again, the model fits better than the original model, which explains 48%. This model explains 54.4% of the data, right? So it explains more, and the quadratic term is very significant. So if you would write down this in a publication, you would say that the ozone temperature is 305.5 minus 9.6 times the temperature plus 0.78 times the temperature to the power of 2. Right, so because these are just the parameters that we get from here. So let's plot this regression coefficient, right? Because we can easily plot this as well because we have a quadratic term. So what we can say is we just plot the ozone versus the temperature, right? So we plot the dots, and then we now say make a curve, right? Oh, and here we say the curve is 305.5, which is the intercept at 0, and for every unit in x you go 9.6 units up, and for every squared unit of x you go up 0.078. And then here we see our linear regression line. And you can see that this is not a straight line anymore. But this line fits the data pretty well, right? You actually see that it goes down a little bit in the beginning because this minus 9x term has a bigger influence than the quadratic term, but in the long term the quadratic term seems to kind of it wins from the linear minus 9.6 times x term. Good, so this is how you do quadratic regression in R, very similar to doing standard linear regression. So the question now becomes is we made a lot of models, right? So we made a model where we say that the temperature is the only thing influencing the ozone concentration. We made a model where we say the temperature and the wind have an influence. So which one is true? So none of them are true. But the one that is the best model is given to us by Occam's razor. So Occam's razor is the statement which was done originally in Latin, and it is frusta fit per plura quod potest fieri per pauciora. And in English this translates, it is futile to do with more things that which can be done with fewer. And this is a basic rule in science. So science always prefers the simplest explanation that is consistent with the data available at a given time, right? So we should not use parameters unless parameters significantly improve our fit of our predictions towards our observations. So how can we now have a formal approach to decide which model is the best? Well, model selection is the task of selecting a statistical model from a set of candidate models. So in this case we have 3 or 4 candidate models that we made: temperature, temperature plus wind, temperature, wind plus the interaction. And we can now use the Akaki information criterion, also called AIC, which is a relative comparison of models. But you have to remember that the AIC, just like the BIC or the log likelihood, is not a statistical test. It is a guideline, like the Pirates guideline is a guideline, right? So the AIC, what it does is that it rewards the goodness of fit as assessed by the likelihood function, but it also includes a penalty that is an increasing function of the number of estimated parameters. So the more parameters you fit in your model, the more the model is penalized for having multiple parameters, right? Just like Occam's razor. It's better to have a very simple model which fits relatively well than have a very complex model which just fits slightly better. In the end, we want to have the best model, which is the simplest model, which explains our observations. So the AIC is defined as 2 times k. So k here is the is again the number of estimated parameters in the model, and to that, or from that, we subtract 2 times the likelihood of L. So you can see that k here is positive, right? And I told you guys that the AIC is actually penalizing based on the number of estimated parameters. And this is because the AIC, when you look at an AIC number, a lower AIC number is better than a higher number, right? So L is the maximum fit of the likelihood function, so it's a goodness of fit estimate, and K is the number of estimated parameters in the model. So the preferred model is the one with the minimum AIC value, not the maximum AIC value. And for a model to be better than another model, it needs to drop at least 10 AIC points. And this is very under discussion among statisticians. Some statisticians say, well, if it drops like 5 points, I already find it that it's a significant improvement. Some people say, well, if it drops 2 units, I already find it a significant improvement. So this is very up for debate. However, in my mind, 10 units is the absolute minimum drop before I'm going to consider a model which is more complex over a model which is simpler. So in R, we can just use the AIC function very easily, which takes a number of models and then it compares these models. So it calculates the likelihood, it looks at the number of estimated parameters, and then just calculates the AIC for you. So for example, here we have the model where we say ozone by temperature plus wind plus the interaction, and then we have our last model where we said that ozone temperature, the ozone concentration is determined by the temperature plus the temperature squared. So if we then do the AIC of the 3 models that we looked at, then we get an overview which looks like this. So it tells us that the worst model is actually model 1. The model that is slightly better is actually model number 3, but the best model is model number 2. And you can see that the drop from the worst model to the best model is around 32 points. So we are going to prefer model 2, even though it is more complex, right? It includes a temperature, it includes the wind and the interaction between the two, but it drops enough to be considered as the winning model in our case. Good. So in conclusion, all models that you make are wrong. And this statement, all models are wrong, it's just that some of them are useful. And this statement is generally attributed to George Box. And with this, I would like to thank you all for your attention. And if there are any questions about linear models, standard linear models, quadratic regression, or using interaction terms, then if you have a question, just throw it in chat. But that's what I wanted to tell you guys for today. So next week we will talk about linear mixed models, so models where we have repeated observations of the same individual. And then the week afterwards we will be talking extensively about generalized linear models or generalized linear mixed models. And this is when your distribution of your input data is not, well, not Gaussian, but when it is not a continuous variable. For example, when you have a binary outcome, someone dies or survives, or when someone or Poisson variable, for example, where you have counted data, like the number of bees on a flower, right? So if you want to do a prediction for that, then you cannot use standard linear models. Davide, I had to leave. Great lecture as always. Have the best weekend. Yeah, Davide, you too. Thanks for being here. Thanks for being until the end. I can understand people not spending the whole afternoon just watching the lecture. Like, the weather is so beautiful that if I could, I would be outside near a puddle of water as well. But unfortunately, or fortunately, I can give you guys the lecture. So thank you for being here, and I hope you guys learned something. So linear regression, one of the core algorithms in more or less predictive biology, but also in machine learning. Machine learning, when you think about like artificial neurons, they use linear regression internally to kind of find the best fit of the input towards the output. Leonardo, thank you very much. Yeah, thank you guys for being here. I always like doing this lecture. It's a little bit intensive, I think, because you're trying to cram so much into a very little time. But thank you guys for being here. This course wouldn't be possible without you guys, right? If there would be no one to ask questions, it would just be me doing the exact same thing as last year. And so your questions are the thing that makes the lecture different from last year and makes it more interesting, I think. All right, so with that, 20 minutes before time, so I didn't really have to speed up, but that's good. All right, see you next week. Time to cook. Yeah, enjoy your dinner, Misha, and already enjoy your weekend. We'll definitely talk over the weekend. So good. Then enjoy the rest of the day, and I will see you guys next time. And thank you for being here. Thank you for listening, and enjoy your pizza. Yeah, it'll probably be pizza again because it's Thursday. Thursday is pizza day. So, okay. Thank you guys and see you next time.